We're officially learning.
Just give me a thumbs up.
Just give you a thumbs up.
The moonshine lecture. You can't just toss that thing out and just blow it on you.
Okay, I will see what, if anything, I can come up with for Monstrous Moonshine by Thursday. All right. Okay, so unfortunately, today is going to be anything but entertaining. Today we are going deep into the weeds of finishing up QED calculations. So these are the things we have to do before we get to the really fun and cool stuff. So just bear with me. And it's already 5:30. It is ridiculous. I have 45 minutes to finish this. It's ridiculous. Okay. Okay. So does anybody know what that expression is for?
Average. Spin averaged.
Yes, it is the spin averaged amplitude for electron-muon scattering. And I want to just point out a couple of things that if you're not careful, you can screw up. This expression is intimately tied to this particular diagram and this assignment of momenta. Okay, if you were to try and do this and accidentally called this P3 and this P4, that expression no longer applies. I mean, of course, you can permute the labels. Okay, but everything hangs on the particular diagram and the labeling scheme you've drawn. So I often find it's useful to keep using the same designation of labels whenever you can. So for example, in the homework, you looked at a variation of this where you took a muon and you flipped it over to this side. And then in the quiz, you looked at a variation where you took two of these and moved them to this side. And so for kind of seeing how you could get one expression for M from the other, it helps to try and keep your momentum labels consistent as you look at different variations. But that's just this piece of advice from someone who's not done it that way and really gotten screwed. Okay, so we have applied what is formerly known as Casimir's trick. And that is when we would do the spin averaging, which of course we get by starting with spin summing, we found that we could replace certain spinor sandwiches by corresponding, and of course you're squaring M, so then you get this. And you could make a replacement of this by a corresponding trace expression. And that replacement itself is affecting the sum. And then we have this factor of 4 because we have 4 possible incoming spin states. And so this affects the averaging over incoming spin states. So now what we want to do is we actually want to take that expression and we want to try and evaluate it more explicitly. Because after all, I mean, this, what is this? This is a trace over spin space. How do I evaluate that? What do I do? Okay, so here we go. You've seen these before. You probably actually derived these. And now we're going to see why you did it. So there are various useful relationships for traces of gamma matrices. And I will remind you of 3 in particular that are going to be useful. So if I'm taking the trace over a product of 4 gamma matrices, then this gives me this funny combination of a bunch of metric factors. And I'm going to do my best to write alpha or etas, but if I slip and write a G, just let me know. And this expression should be marginally familiar to you. Okay, does everybody vaguely remember that? In fact, I think you saw that on your last quiz. Right? Everybody remember that? Okay, good. I don't really know what's going on with Kowalski back there, but anyway, notice this is a trace over spin space. These are all matrices in spin space, so a product of 4 matrices in spin space is a matrix in spin space, and this is the trace over that resulting matrix. The one that might be a little easier to remember is if you have a product of 3 gamma matrices and you take the trace, what do you get?
0.
0, exactly. And then if we take a product of 2, then we just get 4 times the metric, or the inverse metric actually. It's the same components as the metric in flat space, so not such a big deal. Okay, so how are we going to use this? Well, let's just grab one of these trace expressions Okay, so if we can figure out how to evaluate one of them, chances are we're going to be able to just write down the other one. So let's grab one of these trace expressions and use these trace results to see if we can actually whittle that down to something a little more concrete. So if I grab the first one, does everybody remember what gamma bar was defined to be? It's good. I'm glad you guys are really absorbing this material as much as I really want you to.
I have it in my notes.
Okay, so the first thing we're going to do is use the distributivity of the trace. So this is just a, if you multiply this out, this would be a sum of terms. You guys on board?
We don't remember what the bar is.
Is it gamma 0, gamma?
I'll remind you in a minute. I'll write it down explicitly. So first of all, this is just a sum of a bunch of matrices inside these brackets, right? Everybody agree?
Yep.
And if I have the trace of a sum of matrices, that distributes to the sum of the traces of the matrices. Okay? So if I actually break this up, I'm going to have the following sum of traces. So I have trace gamma mu, p slash, oh, that's most unfortunate. Oh, no, it's fine, it's fine. I'm actually, for the sake of being generic, I'm just going to call these A and B, and then later we could take A to B1, B to B2, or so forth and so on. But just so I don't get confused with what I've got written in my notes, I'm just going to call these A and B for now. So yeah, if I distribute these, then I'm going to have the following. Should be gamma bar then. Oh, yep, no, okay. So I'm going to go ahead and identify what this is. So gamma bar lambda is defined to be, so the bar of anything is gamma 0 times the Hermitian conjugate of that thing. In this case, it's gamma lambda, so we take the Hermitian conjugate of lambda. Okay, so anyway, all right, I don't really know where I'm going with this. Okay, so that's the definition of bar. So bar is gamma 0, gamma dagger, gamma 0. Okay, that's bar. However, if the thing you're barring happens to be just a gamma matrix, then this actually turns out to just be the gamma matrix itself. That is not generically the case for an arbitrary spin matrix. But if the spin matrix happens to be a single gamma matrix itself, then the bar form actually returns the original thing. And you can verify that explicitly. Okay? So don't think that this is a robust conclusion. All right? In this particular calculation, of course, that's what the bar is. That's not always what you're going to get when you do these calculations. Because sometimes you might have a propagator sitting in one of these expressions, and so that's going to be part of this capital gamma. Okay, so with that in mind, everywhere I see gamma bar, I can just replace it with gamma lambda, and so continuing right along. Gamma mu, p slash a, gamma lambda, m, b, c. Gamma mu, m, a, c, gamma lambda, p slash b, plus the trace, m, a, c, gamma lambda, m, b, c. Okay? So you squint your eyes just right, you can kind of see where if you multiplied this out and then just looked at it as a sum of terms, distributed the trace, you would roughly get that. You could at least look at one of these terms and figure out where it's coming from if you don't want to write all the details down. Okay. Now comes the interesting part. Every time I see a p slash, what is that secretly? Yeah, so a p slash, so for example, this pa slash is secretly something like gamma alpha p a alpha. Okay? Now, these PAs, what are they in spin space? They're just scalars in spin space. So in particular, you can pull them outside of the trace if you like. Okay? So if you think about each of these terms for a moment, you'll realize that in this expression, will sorry. In this expression, how many gamma matrices are there?
Like 6? No. 4. Okay.
You asking or telling?
Asking Steve-O.
It's not Steve-O's card, baby.
Don't you still have 4 gamma matrices in each PA?
So each of these P slashes has a gamma.
Yeah.
So a gamma, a gamma, a gamma, a gamma. How many times did I say gamma?
Oh, 4.
4 times, good. So this is secretly 4 gammas. Good Lord. Caleb, how many gammas are in here?
I'm gonna go with 3.
3, good job. 3 gammas. And let's see, Brooks. How many gammas are in here?
3.
3, nice. You guys have really upped your game on this. And then last but not least, is Daniel here? No, Daniel's not here. Spencer. How many gammas are in here? 2, good. 2 gammas. Okay? So remember, everything that's not a gamma, you can pull out of the trace. So this is literally a trace of 4 gammas, a trace of 3 gammas, 3 gammas, 2 gammas. Well, what do I know about these 2 parts? They're 0, right, because the trace of 3 gammas is 0. So I can immediately cancel off those 2 things. All right? And then I can write what's left over as PA, and I'm just going to give this I'm going to call the index here alpha and beta just to give them labels. PA alpha, PB beta, trace of gamma mu. Oh no, I should look at my paper. That's what I should look at because I'm never going to write this down right. 1 minute, yeah. Oh, I did. It's alpha beta. I did it exactly right. That's awesome. Because if you just arbitrarily pick these letters and don't have it written down, you're never going to get it right. So there we go. Okay, so this is the first term. Everybody understand?
Yes.
Okay, good. And then the last term, the m's and the c's are all constant, so we ma, mb, c squared, and then trace of gamma mu, gamma lambda. Okay. Now I am in a position to directly apply rules A and C. Joe, Bales.
Are there not, so when we've previously been looking at the MC quantities, we've had implied identities attached to them, making them spin space matrices.
Sure, and you can leave that identity in there.
So we just ignore that as a, yeah, okay.
Yeah, and I mean, having an identity inside of here is not going to change
matter at all.
anything.
Just
Yes.
making sure that those don't impact any of the
Yeah.
spin space matrices. Thanks.
Okay. We're good? Now, a place where you would have to be careful about that, and we're not going to encounter it here, but if you had an expression like this, and I'm going to write this, and then maybe I'll be regretful of it later on, but if I had something like this, where I had like trace of P slash plus MC, okay?
Yeah.
And then this would be trace of P slash plus trace of MC. And then I would have to remember that this is the trace of the identity, which is not 1. Here, the 1 is multiplying things, so it's not going to really change anything. But here, in an expression like this, I'd have to remember it to be careful. Okay? So, good point. All right, so now we just plug and chug. Man. If I say that on Thursday. Oh man, plug and chug. I think that's going to be the name of the lecture. For those of you who don't know what we're talking about, you just wait. Shit's going to get real. Okay, so they're the exact same labels that I have here. Isn't that convenient? So I can literally wholesale strip this expression. And mu alpha eta lambda beta minus eta mu lambda. I hope you're all writing this down or at least processing it because you get through the next step. And then plus, what did I say? Oh, MA, MB, C squared, trace gamma mu gamma lambda is just going to be 4 eta mu lambda. All right? Because you're all snarky and you just let me do all the writing, I want you to now take this expression and I want you to reduce it to a series of dot products. Do it. First person that gets it, come up front and write it down.
That's a fun.
That's not a punishment. You go band side. No. Right. Right. Is that a what? That's a 4. There are no sides in these expressions.
Context.
Now,
You're supposed to be writing this in terms of dot products.
you're actually doing what you were supposed to do on your quiz last week.
Oh, wait.
Yeah, what? Oh. Yeah, now we screw this up. Now we screw this up. It's,
Oh, goodness. Oh, like you lambda?
But I guess that is.
no, it's fine, it's fine. Yeah, no, it's true. If this 3 was distributed in the matrix, it would be 3, 3, 3, and the trace would have those up. Okay, if you pull the 3 out, and you multiply it, then the trace would be 3.
Just one of his sick jokes.
There's a context where I've screwed that. I think I screwed that up somewhere in GR. Anybody got it?
Almost.
Almost? Kowalski, you got it? Kowalski, come to the front and write the answer. Your card was next.
Was it though?
Yeah, it was. It was.
Okay. Well, that's acceptable.
All right. Real time here. Let's let you see what it feels like
Yeah,
to
just
be Uncle Alex.
I think you have the.
Except I have the answer.
Yeah, that's what I was gonna say. It's a
So much
little
better.
nicer.
What are you writing? I don't even understand what you're writing.
I was just gonna do this all out.
You're distributing it like.
Does that know?
That was not what I was supposed to do.
No.
All right.
Go sit down, Kowalski.
Sounds good. My bad.
It was us.
Whoops.
Are you pre-gaming that early? No. Hi. Okay. So, I'm just kidding with you. A little bit. Okay. I'm just gonna read off my expression. I'm gonna cheat. No, seriously. Okay. So here, if I take the first pair, the alpha is just going to raise the index on this guy, so that's going to be a PA mu. The eta lambda beta is just going to raise. I know you were writing it correctly, and I was being an ass. But I feel like for pedagogy purposes, I just need to write this down and do my job. Okay, so the eta mu lambda is not doing anything here, so I just keep it. And then the eta alpha beta is actually forming the dot product here, so I could write that as PA.PB. And then. Say it again?
They're talking trash about me. It's not right. It's fine. It's
Oh, yeah. Well, but you weren't doing it with style. You gotta kind of like. I'm kidding. You were doing a great job, Matt Kowalski. You're my favorite student in the whole class.
Oh, wow.
If everybody left the room except for you. Okay. So the eta alpha lambda is going to grab this and raise it up to be a lambda. And the eta mu beta is going to grab that and raise it up to be a mu. I'd already written P. Man, this is not my best day. Okay, and be careful because the ordering matters. This term is not quite the same as this term because what gets mu and what gets lambda is not the same in those two expressions. And then go MA, MB, C squared times 4. Eta mu lambda comes along for the ride. And then notice, as we should expect, everything carries an upper mu and an upper lambda. As they should, because we're adding all these terms together. Okay, So, what this means is that we can take an expression like this, and we can plug that expression in for each of these traces. Okay? And you've got to be very careful because, you're going to, in the first case, associate A with 1 and A with 1 and B with 3. But then you're also going to associate mu with mu and lambda with lambda. But when you come here and you want to use this expression, you do A is 2, B is 4, and then everywhere you see a mu, turn it into a nu, and everywhere you see a lambda, turn it into an alpha, because we have to use the indices as they appear here. Okay, so everybody understand, like, you got to be a little bit careful in applying this, but otherwise relatively straightforward. And so if we do that, then we're going to get two big terms that we're then going to multiply together. And then I'm just going to write the result of that. So at this stage, what we would do would be plug and chug. And you would get two of those big nasties multiplied together. And so in the end, your expression for the spin averaged amplitude squared is going to reduce to something like this. 8 GE to the fourth, P4 minus P2 to the fourth, and then P1 dot P2, P3 dot P4. And I'm now doing this relevant to this expression, so all my labels are 1, 2, 3, 4, and so forth. Plus P1 dot P4, P2 dot P3. And correcting the typo, P1 dot P3, mass of the electron squared. C squared minus P2 dot P4 squared, it is not squared, M mu squared C squared, and then plus 2 M E squared M mu squared 4. Okay?
So much better.
Okay, it's big, it's ugly, but it's completely trivial in spin space. It's just a bunch of momenta. I mean, these are all 4 momenta, but 4 momenta are just energy and spatial momenta, right? So this is literally an expression in terms of the kind of kinematic quantities that we typically use to describe scattering processes. All right? So there's kind of nothing mysterious about it. All right. Now, we, as theorists, might say, I calculated the amplitude. You experimentalists go and actually figure out like what you actually want to measure, but we're going to do that. We're going to be true to what the experimentalists would actually want us to provide to them. And so you might recall that this is a two-body decay, or a two-body scattering process, sorry. And if we evaluate the differential scattering cross-section in the center of momentum frame, then it takes a particularly simple form. So remember, to calculate scattering amplitudes or decay rates, normally we have to use Fermi's golden rule, which has got a lot of integrals and a lot of factors, but there were 2 situations where that simplified. One was a two-body decay, where one thing decays into 2 things, and the other was two-body scattering in the center of momentum frame, where you have 2 things come in and 2 things come out. And the reason it simplifies is in the center of momentum frame, everything is back-to-back, okay? So in that particularly simple case, the differential scattering cross-section took this form. Okay, where obviously this is the energies of the incoming particles. This is that combinatorial factor for the number of identical particles that we have coming in. Of course, in this case, these are distinct, so the S would just be 1. This is m squared, obviously, and then this is the momentum of either outgoing particle. It doesn't matter which one you pick because their center momentum, they have equal and opposite momentum. So the PFs would be the same whether you picked 4 or 3, and similarly, it doesn't matter which incoming particle you pick. Okay? So what we're going to do is to actually evaluate this. And by the way, if we want to actually evaluate, so just as a technical aside, this expression as it stands is correct, but this expression as it stands would be useful if we were actually going to identify the spin states of the incoming and outgoing particles that we want to measure. We don't do that. So what we would typically want to do is do the spin averaged version, and the only thing that that really affects is that we would use the spin averaged amplitude. Okay? Because the spin part of this story is all sitting in M. None of this other stuff cares about spin. Okay, so we've got an electron and a muon. An electron and muons have a nice property. Muons are much larger than electrons, so we have a nice approximation that we can make. And we're going to say that the energy of E2, which is of course the energy of the electron, we're going to say that our electron has got an overall total energy that's much smaller than the rest energy of the muon. Now that's not true in general. You could accelerate an electron to an energy close to the rest energy of a muon. I'm just going to make a relatively simple approximation. And so we're going to say that the energy of the incoming electron is much smaller than mc squared. Okay. So in that case, E1 plus E2 is approximately the mass of the muon, c squared, plus E2, which is approximately the mass of the muon, c squared. Okay? Now, why did I write this? Why did I say that the mass of the energy of particle 1 is essentially the rest mass energy of the muon? Let me pick a card. Martin. Why would I argue that in this scenario, the energy of the incoming muon is roughly its rest mass energy?
Because for it to interact with an electron, it has to be going not very fast.
No, a muon could interact with an electron going very, very fast. I hear you whispering the secret words. What are they?
I would say because it's massive, because it's like a lot bigger than material.
What does that influence?
Momentum.
What about momentum?
Opposites, so the law cancel, so it has to be like.
So you're in the center of momentum frame. So if I consider a tennis ball colliding with the Earth, and I want to describe that collision in the center of momentum frame, the Earth is at rest the whole time. Okay? Same here. The muon is so much more massive than the electron that the center of momentum frame is the frame where the muon pretty much sits at rest the whole time. So the only energy for the muon we have to worry about is its rest mass energy, but then we said that that's going to be way larger than the energy of the electron, and so the total energy of the system coming in is just going to be roughly the rest mass energy of the muon. Okay. So in that case, this simplifies just a little bit. So again, our S factor is just going to be 1. Yes. Okay. So if we are sending in an electron and it's sort of scattering elastically off of an infinitely massive muon, how does the incoming momentum compare to the outgoing momentum in terms of magnitudes? They're equal in magnitude, opposite. So we can say that P final magnitude is essentially the same as P initial magnitude. Okay, so this ratio is just going to be 1. S is 1. E is MUC squared, so this is just going to be quantity squared. Okay? All right? Now we've evaluated this expression. Okay? It's right here. So if I wanted to calculate, oh man, I could do that. If I wanted to calculate this, I would just take that and multiply it by h bar c over 8 pi m mu squared c to the 4th times that, and I'm done. Okay? So that's my d sigma d omega. But of course, that's not really that useful because, you know, what intuition do you have for that big ass series of dot products? That's not very good. So we actually want to really make this explicit as possible. So now let's actually assign some 4 momentum vectors to describe this, okay? All right, so if I actually set this up so that it looked like the following, I could say, all right, I've got a massive muon that's sitting at rest. That's my particle 1. The electron is going to enter from the left with an energy, I'm just going to call it E, because really and truthfully, that's the only energy we need to worry about, because the energy of the muon is always just going to be the rest energy. So instead of saying E1 and E2, let's just use an E for the electron, and then for the muon, it will always use the rest energy. So I'm going to have an E and a P2 spatial momentum, okay? And then afterwards, we're going to have, again, the muon sitting at rest, and then we're going to have the electron scattering off at some angle with momentum P4 and some energy E, okay? It's elastic, so the E here is the same as the E here. The P here is the same as the P here, except for direction. They have the same magnitude, but they can have different directions. Okay? All right, so I might as well call the magnitude of the momentum, because it doesn't matter which one I'm referring to, I might as well just call that P.
Alex,
Yeah.
are the P's in the original M
Yeah.
equation, are those vectors or scalars?
The P's here,
Yes.
those are 4 vectors.
Those are for, okay.
Yeah, those are 4 vectors. Now, this is a scalar because this is a 4 vector squared,
Right.
and then these are all dot products.
Yeah.
So at the end of the day, it's a scalar. So we're calculating a number.
Otherwise, we'd have a 1 over 0.
No, they're 4 vectors. Yeah, I mean, I guess, I'm being a little bit sloppy with notation. I should, in principle, be putting in, so the thing is when you write that, that's code for this.
Right.
Okay, so that to the 4th is actually, you can expand that with a bunch of indices contracted with each other, but we're being a little loosey-goosey with notation. If you want me to be more precise, I can keep you here till 9. Anyway, all right, so now what I want to do is actually write down the 4 vectors in question. Okay, to evaluate this, we need P1, P2, P3, P4. Once we've got those vectors, we just bang this thing out. Okay, plug and chug, so to say. So what would my P1 4 vector look like? What would the components of the P1 4 vector look like?
E over C, 0, 0, 0.
Say it again?
You said it, but I guess E over C.
Well, what is E over C if you're at rest?
MU C squared.
M mu C squared over C.
MU C.
Yeah, good. We're going to get there eventually. Okay? If you're in your rest frame, your energy is your rest mass energy, but it's E over C, so there's only 1 C here, and then your spatial momentum is 0. Okay? So what is our P3 4 vector? Same thing. It's the muon, so it's just still sitting there. Okay, and now we've got our P2 4 vector. What would that be? I heard it. The P2 4 vector. So now I have a particle that's moving. It has energy E. What's the time component of the 4 vector? It's E over C. So this is E over C, and then the spatial momentum P2. And then P4 would be E over C, the spatial momentum of 4. Yeah, Michelle?
Should we have minus? Because it's a dual vector?
So yeah, I'm writing these as vectors. I know I'm writing them across. Okay, so you should think of these as vectors, and then I agree with you, when we take the dual, we'll put a minus in front of the momenta everywhere. In principle, I should be writing the vectors as columns, but I'm not actually going to write row times column. I'm just going to do this sort of, in our heads. So let's actually do a couple of examples, and then you'll see where that minus is going to pop up. Okay, so let's start with So what do we have to evaluate here? Well, we gotta write down an expression for P4 minus P2 squared. Okay, no one squared again. We've got to get this set of dot products, this product of dot products. We got to get this dot product, this dot product. Okay, so all of those things need to be evaluated. But you have the explicit 4 vectors. Okay, so for example, just picking on one of these, if I do P1 dot P3, which is relevant for this term, what do I get?
mu squared c.
Yeah, I just get m mu squared c squared because I take the product of the time-like terms. Because in our new metric convention, the metric is 1, minus 1, minus 1, minus 1. So the time-like term doesn't get a minus sign. So the product here was literally just the product of the first terms. There's a minus sign on one of the spatial, but who cares? It's 0. Okay. Another one that we need is P2.P4. Well, P2.P4 e squared over c squared minus P2.P4. Okay, there's the minus you wanted to show. We good? We need that term for this. And then I'm going to need these, and I'm just going to write down the results. Turns out that this term and this term actually have the same result. And that turns out to be the mass of the electron squared, c squared. No, sorry. No, hold on. Yeah. Oh, no. Yeah, that's not that. This is the mass of the muon squared times e squared. Okay. Okay, so before I move on, this term can be massaged, and the massaging is in the notes, so I'm not going to write it down. It's just it's about 4 lines. But this term can be massaged a little bit into the following form. Mass of the electron squared, c squared plus 2 times the magnitude of the spatial momentum squared times the sine squared of theta over 2. Okay? Again, it's not completely obvious how you go from here to here, but I've got it written up with the notes. You can look at it if you like. That's a mu right there if you're wondering. I hear rumbling. Is there a question?
We couldn't tell if you were P1, P2, P2, P4, or P1, P2, P3,
P1, P2, P3, P4. I'm just copying these terms down. And then P1, P4, P2, P3. Yeah. Okay. And then last but not least is P4 minus P2. And for the sake of time, I'm just going to write down the answer, and the details are in the notes. So that you can actually determine that this is minus 4 times the spatial momentum squared times sine squared theta over 2. Okay, I tend to write the spatial momentum with a vector hat over it just to remind you it's only spatial. It's not a 4 momentum.
Sine theta, the scattering angle?
Yes, so sorry, yeah, theta is the scattering angle. Okay, and then this is just P without a label, because if you're squaring it, you're just looking at its magnitude, but the magnitudes of all of the momenta are the same, so I no longer have to really label the spatial momentum. Okay? And then we can take all of this, all 4 of these, and plug them into this expression in the various places that they appear. And at the end of the day, if we do that, we find for the spin averaged expression for the differential scattering cross-section, we get something that looks like the following. GE squared h bar over 8 pi times the magnitude of the spatial momentum squared times sine squared of theta over 2 times the quantity ME c squared plus the magnitude of the spatial momentum squared times cosine squared theta over 2. Quite a bit of work, not hard work, but just plugging all of these into this expression and then canceling terms and using a trigonometric identity to replace this sine squared with a cosine squared term. You'll eventually break it down to this form. All right. And this is what experimentalists like. This is called the Mott formula. Okay, so what does it say? Well, first of all, it says if I set up my experiment like this, I take a muon at rest, and I slam it head-on with an electron. This is giving me the scattering cross-section as a function of angle theta. Now, we expect theta dependence, right? We expect to see fewer scattering events or we expect the number of scattering events to change as we, for example, increase theta. Okay? However, we don't expect it to depend on the azimuthal angle phi. All right? In principle, the d omega here includes phi, includes the angle going around the axis, but we don't expect any phi dependence, and we don't see it in the final result. Okay? If you take a limit where the incoming electron is non-relativistic, so that means that its spatial momentum is considerably smaller than its mass times c squared. Okay, that's one way of stating the non-relativistic limit. Then this simplifies to a slightly different expression. And don't worry if none of this really makes sense, because you're going to get to see the details in your homework. And this becomes e squared, where e is the electron charge. I'm writing this in terms from which you might have seen this before. V squared sine squared theta over 2. Quantity squared. Does that look vaguely familiar? That v is just the velocity of the incoming electron. Remember, folks, just because there's so many details, when I write p spatial in an expression like this, that's a relativistic momentum. It's the relativistic spatial momentum. So this is not mv. Okay? But when I take a non-relativistic limit, I'm now working with the non-relativistic spatial momentum, which is just mv. Okay? So part of connecting this to its non-relativistic limit is realizing that. Does anybody recognize this expression?
I feel like we used that in MATLAB 2 before.
You probably did. And does anybody remember the name associated with it? Yeah, this is Rutherford. So Rutherford scattering described by the Rutherford formula.
Yeah. Hey, genius, what the heck?
Okay? Yeah, Jacob.
So in Rutherford's experiment, or really it was a Geiger's experiment that Rutherford stole, it was, they weren't shooting the particles relativistically. They were just,
I mean, so you could use the Mott formula if you want to do a relativistic scattering event, but no. Okay, so I have a question for you. So this obviously is somewhat useful, right? I mean, non-relativistic scattering of an electron hitting a stationary muon. If we want to crank up the energy of that electron, eventually we're probably going to get to the point where we really need to take into account the relativistic corrections, and so we would use the Mott formula. Is the Mott formula the right answer? Why? Because we what?
Made so many assumptions.
we didn't use.
Okay, good. So I hear a couple of things. So what all corrections would we have to take into account to get a better result than the Mott formula?
More diagrams.
Exactly. So that's one thing. We only used one diagram. This is one of how many diagrams that we should actually be, yes, an infinite number of diagrams that we should actually be calculating. Okay? Also, we did take some approximations based on the relative masses. Okay? So you can kind of see where this enterprise could get really hairy really fast. All right? So we're not, I don't feel like this is like the sexiest thing, all right? But this is incredibly important if you want to connect these tools to actual experiment. Okay, now I mean, don't get me wrong, if you're an experimental particle physicist, it's not like you do this calculation every day. You do harder work. So But no. So, I mean, nowadays there's packages that cram all this, that can do a lot of this for you. What we really want to do is think about some diagrams which give us more interesting results that lead to deeper insights. And so to that end, there is a couple of tools for evaluating QED Feynman diagrams that I have to give you that we haven't actually covered so far because they haven't come up in any of the diagrams. Kowalski, ask a question.
Yeah. So when we average over spin states in general.
We have what?
When we average over spin states,
Yeah.
is it always fair to say that each spin state has equal weight?
Yeah, sure. You're sending in an unpolarized beam.
Okay, sure.
That's the idea. So in an unpolarized beam, every possibility is realized with equal probability.
Fair enough, but you can definitely send in other beams.
Yes. If you want to do polarized beam experiments, which some people do, then you're not using the spin averaged expressions.
Right, and
Yeah.
there's different anti-spin.
All right. So there's one diagram contribution which we have not covered, and it actually poses a correction to this calculation that we just did. So if we consider electron-muon scattering, among other corrections, we could imagine that as the photon is exchanged between the two electrons, it pauses and burps a particle-antiparticle pair. Okay? And in the burping of this particle-antiparticle pair, I could, for example, and I'm just going to label everything so that I can actually write down the quantity. So I'm going to keep these external momentum labels the same, so you can take this amplitude and you can directly add it to the previous one that we wrote. Okay, I'm going to have my Q flow up. And now we just got to be, let's be a little bit sensible. If this is Q, I could call this Q1 and I could call this Q2. Look at what I'm pointing at. I could call this Q1 and I could call this Q2. And then I know that when I go and calculate M, I'm going to do a delta function here for momenta, a delta function here for momenta, one here for momenta, one here for momenta. But then when I use those delta functions to evaluate the Qs, what's it going to do to the momentum here and the momentum here? It's going to set them to the same value. So I might as well just be sensible and call this Q as well. Okay? In fact, it gets better because I could call this a new momentum and this another new momentum, or I could just call this a momentum K and then call this a momentum Q minus K. Okay? Because think about it, at this vertex I have Q coming in, I have, oh no, hold on. I chose my, oh sorry, K minus Q. I did it exactly backwards. K minus Q. Okay? So at this vertex I have Q coming in, I have K minus Q coming in, so the total is K, but I have K going out. So I'm being smart with my labeling and I'm going ahead and conserving momentum. When you can. It's typically easier to do with purely internal things. Okay? So with that labeling in mind, what I'm actually calculating now is the one loop correction to electron-muon scattering. It's one loop because there's one completely isolated internal loop. Do we expect this contribution to be larger and smaller than the one we calculated previously?
Smaller.
Why?
More vertices.
Yeah, because that is the consequence of it being smaller, is that it has less of a... Well, again, does this happen? Everything happens. It's the question, Kowalski, is how much of a contribution does it make?
Right.
This is the difference between this and the diagram I evaluated previously is what's going on virtually. We never ask what happens virtually. It's just a matter of how much do they contribute to the total M. This would have a smaller contribution because it's fourth order in the vertices. Okay?
So just more vertices equal less chance of it happening, right?
In general, yeah. Well, that's good news because, right, there's an infinite number of terms, but the difference is that as you go out, you get more and more vertices. Okay? Now, all that hangs on the idea of the coupling, the vertex factor being less than 1. If your vertex factor is order 1, you're screwed. Okay? But in QED, the vertex factor is very much less than 1, and so higher orders are. But I'm not showing you this because it's fun to show you higher orders. I want to show you this for an important reason. Okay, so first of all, we do not yet have a tool for evaluating this diagram. There's quite a bit of it we know how to do. We can follow this matter line back in, write down a U bar and then a vertex factor and a U. We can write down a U bar and a vertex factor and a U and get these matter lines. We could put in propagators for these internal photons, but then what do we do about this thing? So you would use matter propagators, but here's the tricky part. Remember, we write down U bar, vertex factor U to make a spinor sandwich to get a scalar. And then similarly here, how are we going to get a scalar out of this?
U bar U.
Well, no, because these are internal. We write down propagators for internal lines. And propagators are matrices. They're not U's or V's or U bars or V bars. Well, you don't have to guess. This is a new rule. I'm going to give you a new rule. So if you encounter an internal loop of pure matter, then the rule is the following. And then I'll write down the expression applying the rule. For internal loops of matter, write down an ordered product of propagators and vertex factors. So that's going to give me an overall matrix in spin space, because every propagator is a matrix in spin space, every vertex factor is a matrix in spin space, and then trace over it. And that'll create a scalar in spin space. Spencer.
Which one of those in the loop is an antiparticle? Which is a particle?
It actually doesn't matter. So in fact, the way I drew the loop, it's a bit odd, right? Because if I draw a loop like this, remember time goes to the right. So if this is the beginning and this is the end, during this part, this is a particle, but during this part, it's an antiparticle. So it turns out we don't really have to distinguish that, because this is important. This is actually a really good question. If we were writing down the U's and the V's, we would need to know. But since we're writing down propagators, it doesn't matter. They all get the same propagator. So don't try to distinguish. You don't need to. You're going to write down the same thing. Okay? So with that in mind, let me just write down what this one loop amplitude is, say a word about it, and we'll get out of here. Okay, so at the end of the day, the one loop amplitude is going to be, and I'm just going to evaluate a lot of stuff here. Is there a person coming, leaving? What's going on at that door?
No.
Waiting.
Guys, you're driving me nuts.
Just wait till Thursday.
You think this is bad?
Are those flashes and cube flashes?
Is that, yeah, what is that?
Quite the little chatterboxes we are today, huh?
Maybe you had a monologue while you wrote this.
You know how hard it is to write and talk at the same time? Okay, so let us not freak out here, okay? Yeah, let's freak out. No, I'm just kidding. Okay, so we see here that we followed 3 vertex factor, that's the gamma mu here, and then 1, okay? And then over here, I've done, and I could have written this chunk, and this chunk in any order. Okay, and then there I see I'm following 4n vertex factor with gamma nu, and then a P2 here, okay? Now, I wrote down propagators for these photons, but the propagators for those photons are really just constants times the metric but I used those factors of the metric to bring down the indices in these gamma matrices. So when I wrote down the propagators, these gammas would have had upper indices because this is a vertex, sorry, not propagators, the vertices. So when I do this internal loop, I would have a vertex factor here and a vertex factor here, but the vertex factor here is connected to the vertex factor there by the metric for the photon propagator here. So if you're wondering where are those metric or where are those photon propagators, I've already used them to lower the indices here. Okay? So what is this expression? Well, first of all, the stuff in the denominator is just a scalar, so it could actually be part of the trace and it wouldn't change anything. So these are from the vertex factors, and then the thing here divided by this is just the propagator for this part of the loop. And the thing here divided by this piece is just the propagator for this part of the loop. And I should say that these are virtual electrons. If I could do virtual muons, virtual tauons, I could do a lot of different things. And that would just change the mass in this contribution.
Does that you have to do all those corrections?
Yeah, you have to do them all. Okay? So does everybody see, and by the way, it's ordered because I do a vertex factor, here, we'll do a vertex factor, a propagator, a vertex factor, a propagator. So vertex factor, propagator, vertex. And you got to do the ordering right because they're matrices. Yes?
Should we have an integral over Q as well?
No. You should not have an integral over Q because Q, all right, Q is actually going to be directly related to the change in momentum from 2 and 4, or the momentum exchanged between these two. So if I think about this particle comes in with some momentum and then it hands off momentum to this particle, the difference in the momentum here and here is how much momentum is exchanged. So what's nice about expressing this as in terms of Q is I could express this momentum exchange in terms of, 2 minus 4 or 1 minus 3. It's kind of a robust expression. But yes, so in a sense, this is an internal momentum, but it's an internal momentum which is completely specified by the external momentum. So I did integrate over it, and I used a delta function, and that delta function set it equal to P2 minus P4, but it also, depending on how the order you did things, it could have also set it equal to P1 minus P2, or P1 minus P3, okay? The reason we like to write it like this, Ariel, is for the following reason. This answer, okay, we can kind of think of as parametrized by the momentum exchange. Now you might say, well, what does that matter? Well, here's an important observation. This integral right here, which we still have to do, that's the integral over k, that's going to diverge. If you actually try and evaluate that integral, you're going to get infinity. So now you've got an interesting problem because the rest of this calculation is going to be finite, that is not 0, but sitting in the middle is a piece which is going to give us infinity for the scattering amplitude. Now, what the hell are we to make of that?
Well, I guess I didn't think of this before, but if you're integrating over momentum, right, K, why can you have infinite momentum?
Why can you?
Yeah, if you're a massive particle, aren't you bounded somewhere?
Oh, that's an interesting question. So Q, the value of Q is fixed by, so remember, when you do the calculation, you fix this momentum, this momentum, this momentum, and this momentum.
Right. And then,
you say, I'm going to slam these two together, I'm going to fix their momenta, and then I want to calculate the probability of this coming out with P4 and this coming out with P3. So those are all fixed.
Right.
And those being fixed fixes Q.
Right.
But K is completely undetermined. If Q was 1 unit of momentum, all I have to do is make sure momentum is conserved. So this K could be 1 billion, and then this would be 1 billion minus 1, and momentum would be conserved in this process.
Yeah, but the relativity would be violated, wouldn't it? Like,
Why?
well,
You take
This is momentum. This is momentum going in one direction and momentum going in the other.
dang it.
Yeah, that's the problem. We have two things going like this. They can have arbitrarily large momentum and the system still have zero momentum.
Yeah.
Okay? The problem here is that exactly what you observed, this is going to diverge because there's no reason to cut k off. K goes to infinity. Okay? So what are we to do with a calculation which is supposed to be a small correction to our previous answer, where the small correction is infinite?
Multiply it by something that is 1 over infinity, just as good.
No. So this whole, sorry Jacob for cutting you off. But this observation, which we will return to in the last week of the course, is the seed for the whole program of renormalization. And it is a systematic way of addressing these infinities, which in the early days of this, these kinds of infinities were encountered early in the 20th century, and a procedure to address them was put in place, but no one was really comfortable with it. I mean, even Feynman wasn't particularly comfortable with the idea of renormalization until at some point in the 60s, a guy named Kenneth Wilson came along, and he actually gave us a very good conceptual understanding of why we have to renormalize things. And that's what we're going to talk about at the very last week of this semester, after we've talked about the strong and weak interactions and how they contribute to renormalization. And the cool thing about renormalization, BTW, is that that is eventually going to lead us to the need for quantum gravity and string theory. More on that later.
Let's go.
Let's go! Go team! Thank you, Spencer.
Yeah.